All right, let's talk limiting reagents. Regardless of where you took your prep chem class, you should be familiar with the concept of a limiting reagent. If you took prep chem at Grossmont, you also should be familiar with the ice table method. But if you didn't take your prep chem at Grossmont, we're going to talk about it right now. All right, so the general idea behind limiting reagents is you only have so much stuff going in. Some reagents are going to be there in just infinite amount. Other reagents are going to be there in excess, but still a finite amount, whereas other reagents are going to run out first. So the classic example I like to give that's very visual is, let's think about you're having a barbecue and you assign every person coming to your barbecue a separate item to bring. You tell one person to bring patties, one to bring buns, one to bring cheese, and one to bring tomatoes. So at your barbecue, everything gets going, you start making the burgers. Each burger takes one bun, one patty, 2 tomatoes, and a piece of cheese. Well, as you get going, think about it. Look at this. What runs out first? The burgers run out first. There's only 3 of them. And everything else there's 4 buns. So there was a 1-to-1 ratio there. There's 6 pieces of cheese. That's also a 1-to-1 ratio. Now the tomatoes is a 2-to-1 because each burger takes 2 tomatoes, but there's 1, 2, 3, 4, 5, 6, 7 tomatoes. So you still run out of burgers before anything else. Okay, and so left over you've got, your patty, or not your patty, your bun, your tomato, and some cheese. And if you've got someone at your barbecue that doesn't like meat, just wants a veggie burger, then you're good to go. Or a cheeseburger, rather. Okay? All right, another example. So, at the time of this filming, I have a 4.5-year-old daughter. She does like to help, which is awesome. And so, one of the things she likes to do is she does, most nights, like to set the table for dinner. When she first was learning how to set the table, she wasn't so sure about what to grab. So sometimes she would just kind of grab a handful of things, right? So in the drawer that's accessible to her, we've got forks and spoons and blunt butter knives, all things that a kid can touch. So she would just grab a handful. Well, in a classic play setting, we've got a fork, a knife, and a spoon. So we want to know, knowing that, how many settings are possible if she grabs 6 forks, 4 spoons, and 7 knives? Which one's limiting? Well, this is where we can start thinking about these ice tables. Okay, so the ice table we're going to refer to as initial change. And then the E can stand for 2 different things. In this situation, the E is going to stand for end. Okay. Later on down the line, when we learn about equilibrium, we're going to need to come back to ice tables because to solve those problems, you have to set these tables up. And in that situation, we're going to refer to it as initial change equilibrium. But it still works. It's still the same acronym, ICE. Okay. All right. So these are our ice tables. So given this, what does this look like? All right, so our reaction equation is fork plus spoon plus knife yields 1 setting. So we start off with 6 forks, 4 spoons, and 7 knives, and we have 0 settings. So at the beginning of a reaction, all right, we're going to assume we've got starting material, but we haven't dumped it all together yet, so we have no product. So we're going to put that 0 there. Now, when we do the ice table, we account for the stoichiometry on this change line. Now I have 1 fork, so I'm going to subtract 1 equivalent of forks. I have 1 spoon. I'm going to subtract 1 equivalent of spoons. I have 1 knife, so I will subtract 1 equivalent of knives. And I'm making 1 place setting, so I add 1 equivalent of place settings because my reactants I'm losing because they're reacting, and my products I'm gaining. So I subtract my reactants and I gain my products. All right? Now, we have to figure out which is our limiting reagent. The limiting reagent is the one that runs out first. So at the end of the reaction, the limiting reagent is the one that equals 0. Okay? So at end of reaction, okay, our limiting reagent whoa, that's weird. Okay. Let's try rewriting this word. Okay, at the end of the reaction, our limiting reagent is going to equal 0 because we've run out of it. Our other reagents should have something left. And so what we do is we do this. We figure out which one is limiting. And so if our limiting reagent goes to 0, we start with our initial minus our change equals 0. And our change we don't know yet. That's x. So we solve for x. And then whichever x is the smallest, that's the one that runs out first. So in this case, it's this one right here. It's our spoon. Our spoon runs out first. So our spoon is our limiting reagent, and our excess reagents are going to be our forks and our knives. And we can make 4 place settings because our setting, we only gained 1x, so 0 plus 4 gives us 4. Okay? When we do these, for this situation, we're working in moles. When we talk about equilibrium later this semester, we'll start looking at things in terms of concentration, or moles per liter. But right now, we're just dealing with moles. All right? So we're going to start off with one that just is in moles, and then we'll work to one that starts off with grams. And then I'll give a few for you to try on your own. All right. So I have 7.5 moles of iron heated with 2 moles of sulfur. And I want to know how many moles of iron 2 sulfide are produced using my ice table. Okay, and so I've got my sulfur. Okay, and we heat it to molten sulfur. Remember sulfur, S8. And then iron 2 sulfide. Okay, and so we start off with that balanced equation, all right? And then we need to build our ice table. I'm going to switch to another slide because I pre-built empty ice tables so that everything would be neat. All right, so on the top here, I've got my sulfur, got my 8 iron, and I've got my 8 iron 2 sulfide. Okay. All right, now from our problem, we're already in moles, so I don't have to do any math to start filling out my table. So I have my initial, I have my change, and I have my end. I still write my change line with a delta instead of a C, because delta also means change. That's the way I learned it when I was a student 25-ish plus years ago. So I still use the delta because that's the way I was trained. If you write a C, it's perfectly fine. Okay, so we started off with 2 moles here, 7.5 moles there, and none there, okay? Now, during our reaction, I have no coefficient in front of the sulfur, so I'm going to lose 1 equivalent. I have 8 in front of iron, so I'm going to lose 8 equivalents. Okay, and I have an 8 in front of iron 2 sulfide, so I'm going to gain 8 equivalents. Okay, so now we need to figure out x. So what would x be if it was from the sulfur? Well, I have 2 minus x would equal 0. And so x equals 2. Okay. All right. What about x from my iron? All right. Well, I have 7.5 minus 8x equals 0. So x equals 0.9375. So what's smaller, 2 or 0.9375? If you said 0.9375, you are correct. So this has to be our x because it's the one that's smaller. So we'll lose 0.9375. We'll lose 8 times 0.9375, and we'll gain 8 times 0.9375. Okay? All right, and so as we do this, 2 minus this, we get 1.0625. We get 0, and we get 7.50. So how many moles of iron 2 sulfide are produced? 7.50 moles of iron 2 sulfide produced. Okay. All right, now let's take a look at one where we're going to start off with grams. All right, so we're going to have to do some converting to moles first. All right, so here I've got ammonia and fluorine. I've got 5 grams of ammonia and 20 grams of fluorine. So we want to know how many grams of hydrogen fluoride gas are produced. Okay, so we need to write our balanced equation. So we get our balanced equation, we get, oh, well, I can write it on this slide because I have space for it. All right, so I'm going to get 2 ammonia. I have 5 fluorine, 1 dinitrogen tetrafluoride, and 6 hydrogen fluoride. Okay. And everything's a gas. All right, so we have our initial, we have our change, and we have our end. So we haven't converted to moles yet, but we do know a few things. We know that we don't have any of this initially. We know from our coefficients we're going to lose 2x, we're going to lose 5x, we're going to gain x, and we're going to gain 6x. We can fill that in without doing any math. Okay, so there's what we know before we start doing math. All right, so we're going to look at 2 things. First, we have to convert to moles, and then we will figure out our x's. So we're going to look at our ammonia. Okay, so for our ammonia, we get 5 grams. And we have 1 mole and 17.03 grams. And we're going to get 0.9 or 29, oops. 0.2936. Okay, and so then I can put that up here, 0.2936. Okay, now I do carry an extra sig fig or 2 while I'm filling out an ice table because of rounding issues. If I'm just doing basic normal stoichiometry, I just carry everything on my calculator and I round off at the end. So when I do an ice table, I always carry an extra digit or 2 just to avoid excessive rounding errors. If you round too much too frequently, then you start to introduce rounding errors. And so since the ice table isn't giving us our final answer yet, we'll round at the end. Okay. All right, and then we'll get some information about our fluorine. Okay, we started off with 20 grams. Okay, 1 mole and 38 grams. All right, and so we get 0.5236 moles of fluorine. Okay. All right, now let's figure out what X is. So for our ammonia, we get 0.2936 minus 2x equals 0. X would equal 0.1468. All right, for fluorine, we get 0.5236 minus 5x would equal 0. So x equals 0.1053. All right, which one's smaller? Fluorine. So this is our x. And now we fill it in. So minus 2 times 0.1053 minus 5 times 0.1053 plus 0.1053 and then plus 6 times 0.1053. All right, so we end up with a tiny bit of ammonia left. We don't have any fluorine left. We have 0.1053 moles of our dinitrogen tetrafluoride and 0.6318 moles of our hydrogen fluoride. Now the problem asks us how much hydrogen fluoride gas in grams we form. So we'll take our 0.6318 moles of hydrogen fluoride And I don't know if you just heard that yell picked up on my microphone, but that is my husband cheering at a soccer game. Times 20.08 grams of hydrogen fluoride in 1 mole. And we get 12.64. And here's where we'll round. Our grams that we were given at the beginning were in 3 sig figs. We're going to round this to 12.6 grams of hydrogen fluoride. Okay? All right, so now, as usual, if you don't practice these, you're not going to learn them. So guess what? I have practice problems for you. Okay, so here's a practice problem. I know my face or my little head cuts off here, so you can grab my slides from Canvas and try the problem. I'm not going to solve the whole thing, but I will give you some final answers. Okay? All right, so try it and then check your work. All right. I'll fill this in at the top for you. All right, so again. All right, so at the very beginning, we'd have 0 minus 4x minus 5x plus 4x and plus 6x. Okay, so I'm not going to give you all the numbers, but I'll give you the end line. So you should end up with 0.0419, limiting reagent of oxygen, 0.0462 of nitrogen monoxide, and 0.0694 moles of water vapor. Okay. Then you're going to produce 1.39 grams of nitrogen monoxide produced. And you'll have 0.714 grams of ammonia produced. All right, so this should give you just enough information for you to try this on your own. That's really messy. And see if you are understanding the ice tables if you've never done them before, or to check to make sure you remember them if you did them last semester. Okay, and I have one more for you. Okay, this one, same deal, it's just 3 reactants instead of 2. Okay, this one's just asking you, it's not asking you how much of anything's left, but we do need to know how many grams of the aluminum chloride can be formed. Okay, so same deal. Hopefully you're not watching this until you tried the problem on your own. All right, because I'm not going to solve the whole thing for you. I'm just going to give you some of the information. Okay. All right. So again, none of this to start with. I'll give you some of this. And I'll give you the very end line. Okay, so that's what it should look like at the end. And then you're going to make 201 grams of aluminum chloride formed. All right, so those are ice tables as usual. If you are stuck, reach out to me and let's talk about these. Try them first though, okay? Don't just say, oh my gosh, I have no idea. Try it first, because I guarantee you it'll be a lot more productive if you come to me and say, okay, I tried it and I got stuck here. All right, because then I can help you a little bit more effectively. Okay, good luck.